Hello and welcome to lab number 9. The title of this lab is Diffuse and Specular Reflections. As the title of the lab indicates, we are learning a little bit more about different types of reflections in this lab. You will see that we have two different types of reflections, so-called specular and diffuse. Specular reflections occur when the light beam strikes the surfaces that are polished, like mirrors or water or polished metal. So we are dealing with a polished or smooth surface. And then the second case, the second type of reflection are so-called diffuse reflections that are taking place on the rough surfaces or surfaces with the texture. So here we are talking about the materials such as paper, wood, fabric, etc. that would usually have a rough surface. So if the surface of an object is polished or glossy or smooth, it will reflect the light much like silver coating on the backside of the glass mirrors. And these so-called specular reflections are actually very important in photonics. A reflected beam that's produced through the specular reflection has almost as much energy as the incident beam, and that's very important from the perspective of laser safety because these secondary reflected beams are as dangerous as primary incident light beams, and as a matter of fact, the most of laser accidents are actually happening as a result of exposure of a human eye to the so-called specular or secondary reflections. So we want to shed a little bit of a light on these types of reflections, both specular and diffuse, learn a little bit more, and then as a hands-on part of the experiment, we are going to observe the reflections from a few different types of a surface, both rough and smooth, and produce both diffuse and specular reflections. The learning outcomes for this lab is to learn about specular and diffuse reflections, to state the difference between them, and then to demonstrate them in the lab environment, and also to learn a little bit more about the potential skin and ocular hazards associated with specular reflections of the laser beams, and also to identify adequate protection and safety measures when working with lasers. Finally, you would also want to do a little bit of exploration about the applications of both specular and diffuse reflections. Here's the equipment that we are going to use in this lab. Red laser diode module, a frosted light bulb. This frosted light bulb should be an incandescent light bulb, and then two small cards, one made out of paper or card with a glossy white surface, another one that imitates a very rough surface. So I used a piece of a paper towel that's been glued to a cardboard, and so that's going to be my card with a rough white surface, and this one has a very glossy smooth white surface. So in this first part of the lab, I mounted my two cards here on the back screen. Remember, I have a card with a rough surface and a card with a smooth surface. So on the left hand side I have a card with rough surface, and on the right hand side I have a card with a smooth surface. And then I also here position my red laser pointer, glued it down to the workbench, and pointed the laser beam to the two cards on the back screen. You can immediately see the difference that laser beam produces on one card compared to the other. On the smooth surface you see a much more clear reflection of the laser beam, while on the rough surface it's kind of more blurry. So again, in the case of card with the rough surface, we have a reflection that is a little bit fuzzy due to the fact that the surface is rough. So this is the case of so-called diffuse reflection. What's happening here is as the laser beam is hitting this surface due to the rough surface, due to the texture, it's been reflected in many different directions based on a specific point at which a laser beam is hitting the surface with a text fixture. So in other words, the law of reflection applies, but the normal is different at different points along this rough surface based on the angle at which incident beam is hitting this rough surface. So the reflected rays are ending up going in all possible directions. The beam is spread out, so the reflected beam is diverging in many different directions. So that's why you see this pretty fuzzy and blurry type of a reflection on a rough surface. As opposed to the rough surface, on a smooth surface, here we have no texture, so the incident light ray, when it hits this surface, it's gonna be reflected in the same direction. So all these different points on the cross-section of a laser beam will be reflected along the same directions. So in this case, we are talking about a reflection at the same angle to the normal as the incident light ray, and this is so-called mirror-like or specular type of a reflection. So once more, specular reflection occurs on all polished or smooth surfaces, and it has a significant importance importance in a case of a laser safety, because if you have a mirror-like or smooth surface, the reflections may have a same effect, same impact on your eye as a direct incident beam. So we are paying a very close attention to so-called specular reflections when we are talking or implementing any kind of laser safety measures. The experiment that I performed here on these small two index cards can be performed in many different ways. You can point the laser beam on a wall of your room, or if you have a popcorn-like type of a ceiling, you can point the laser pointer in that direction as well and see and observe specular reflections. And then you can find any kind of smooth surface. If you have a metal door that's been painted white with a smooth surface, you can point your laser pointer in that direction and see a specular reflection. It's important to mention that if you are performing any kind of experiments where the direction of the beam is not well controlled, meaning it can end up in your eye, it's important to implement proper laser safety measures, meaning you would have to wear proper laser safety goggles to protect your eyes from any kind of unintentional laser beam. In this second part of this lab number 9, we are performing an experiment with frosted incandescent light bulb. We are dealing with an incandescent light bulb, so this is a light source that has an incandescent filament. In other words, the way how this light bulb operates is when you bring the electricity, when you bring the power from your power grid down here, the electrical current is going to flow through the filament made out of tungsten most of the time. And that filament that is inside the glass, inside the light bulb, when it's exposed to the electrical current, is going to heat up. And as it heats up to a specific temperature point, it's going to start glowing, producing light. And that's how this incandescent light bulb works. Now, the fact that the outside of the light bulb is made out of frosted glass doesn't allow us to see what's the inside of the light bulb. So what we want to do is we want to use the laser pointer. So if I take the light bulb in one hand and take my laser pointer into the other hand, and again, it's very important here to implement proper laser safety procedures, not to point the laser pointer into your eyes, and to wear proper laser safety goggles to protect your eyes from any unintentional hit of the laser beam. So what I'm gonna do is I'm gonna take the laser pointer and I'm gonna point it in the direction of my light bulb. And as you can see here, when I'm pointing it in the direction of this light bulb, it's very difficult. You cannot see what's inside due to the reason that the light bulb is made out of frosted glass. So that frosted glass on the inside is blocking the light to go inside, and you cannot see the light filament. However, if you're going from the other side, so if you point your laser pointer from the back of your light bulb, the filament is going to be clearly visible right now as it casts its shadow on the back side of the bulb. Now we can clearly see the filament of the light bulb, or to be more accurate, we are seeing the shadow that the light filament is casting onto the back side of the bulb.